Okay then. So we'll begin the class, guys. Yeah. Okay. So hello everyone from Zoom class and hello everyone from YouTube. Okay. Sir, AC current, when will you start? I'll start soon, bro. But let me complete the part two syllabus. Okay. So part two, I thought it's better to complete part two because it has good amount of weightage and it will take less time to complete also, right? So we can do that very quickly. So we'll finish the part two physics, then we'll come back to part one. Okay. Yep. Good. Cool. Okay. Then. So yesterday we have completed in the last class we completed the chapter of electromagnetic induction, and today we are going to start a new chapter, right? And it's called electromagnetic waves. So it's a very easy chapter, and the probability of you getting question from JE or NET is very high. For example, this chapter consists of two parts. The first part is electromagnetic waves, and the second part is communication system communications system. So there's a very high probability that you'll be getting one question from EMFs for sure, and there's a high probability that you might get one more question from communication systems. So overall total, you might get one or two questions, and that's compulsory. There is no mistake in this. You'll be getting at least one or two questions from this chapter, and hardly it'll take two classes to complete. Electromagnetic waves will be over in one class. Like today, I'm starting the chapter of electromagnetic waves. It'll be completed soon, like before the end of 1.5 hours, right? And tomorrow we'll start with communication systems also. Okay, we'll complete this by tomorrow, and we'll move on to either modern physics or semiconductor or wave optics, like whichever you choose. Okay, wave optics, modern physics, yeah, whichever you choose, we'll move on to the topic. Cool, right? Okay, so shall we begin the class, guys? Then is everybody comfortable here? So I heard that you have exams today. Okay, hope you have done good. Cool. Okay. So we'll move on. Okay, yes, cool. So you might ask me, sir, what is electromagnetic waves and what's its uses? So let me start with the pretty basic concept of this chapter. The first, then the very easiest idea is, for example, imagine a positive charge. Okay, you have a positive charge plus Q. Okay, and if this charge is at rest, it is not moving. This charge is at rest and it is not moving with any velocity. So then this will only have electric field. This will just have electric field around it. Okay, nothing else. Only electric field will be existing for a charge at rest. Okay, then what will happen is when the charge is moving at a constant velocity, for example, imagine this charge is moving at a constant velocity now, then what will happen? So for this charge, there will be electric field also as well as magnetic field along with it. Cool, right? And lastly is what happens is if this charge is moving and the velocity is not constant, rather it is accelerating. Okay, so when it is accelerating and moving, so what will happen is it will have electric field, it will have magnetic field, and also when the charge is accelerating, it will emit radiation. It will emit radiation. So this is what happens, and this is the source of a electromagnetic radiation. Cool, right? Am I clear? So a charge at rest gives out only electric field. Charge moving at constant velocity gives electric and magnetic field as well. And charge, a positive or negative, which is accelerating, will give electric field, magnetic field as well as radiation. Okay. So this is the source of radiation, and this is very important. You should be clear about it. Okay. So any doubt, guys, from this concept, from this slide? Okay. Cool. Yeah. Am I clear? If I'm clear, click on yes, guys. If I'm clear. So should you want me to repeat it again? So let me repeat it again. Okay. So before I move on to next concept, a charge at rest gives out only electric field. A charge at velocity constant gives out electric field as well as magnetic field, and a charge accelerating. An accelerating charge will always use electric field, magnetic field as well as radiation, denoted by this letter gamma. Okay, cool, right? So point one, point two, and point three. Okay, so we already have sufficient knowledge about electric field. This we have studied in the chapter of electrostatics. If you remember, So in electrostatic, we see what happens to a charge, what is the electric field, what is the potential of the charge, what is the potential energy. We have studied enough basics of electrostatics. Next, when charge is moving at constant velocity, remember this, it's very easy here. When charge is moving at a constant velocity, that means it's a current, right? What is current? Current, it is flow of charge. Whenever charge is flowing at constant velocity, have current. When there is current, there is magnetic field also, right? So this we have studied in previous chapter in magnetism and electromagnetic induction, right? Magnetism and electromagnetic induction, we have studied this. So we now are going to dedicate a separate chapter to study this concept. So what will happen? So when a charge is moving at very fast, which is accelerating, it will have electric field, it will have magnetic field, as well as it emits radiation, as I told you, right? So we're going to study about this radiation. So what is this radiation? What kinds of radiations are there? We're going to see as much as possible. Okay, cool, right? And you might have wondered, like if you have ever went to take an X-ray in a doctor's hospital, right? Of course, you take it in a doctor's hospital, right? Yeah. So whenever you go to take X-ray, they have a source which gives X-ray, right? They have a machine which produces X-ray. How do you think that machine will produce X-ray? It will convert that current, okay, into our X-rays. So how does it do? Exactly by this principle of this third idea, right? So what we do is there the current will be creating an electric field, and they inside that electric X-ray machine they have a set of charges. Okay, the different kind of element will be there. They have these charges, and when electric field is applied to these charges, they start accelerating. Okay, these electrons of this atom start accelerating, and when they start to accelerate, they emit X-rays. And when they emit X-rays, if I keep my hand in between this X-ray, what happens is, oh, this is not my hand, by the way. And so what happens is when this X-ray passes through my hand, I get just the skeletal system. I'll just get the skeletal system out of it when I take the photo of the X-ray. Cool, right? So this is a pretty simple idea. So the acceleration is a source of electromagnetic radiation. Okay, and why is it called electromagnetic radiation? Because this radiation will have both electric field and magnetic field. Okay, that is why it's called electromagnetic radiation. Okay, so what is the electromagnetic radiation? Radiation, what is the radiation? Radiation is nothing but a wave kind of energy particle. It's like a wavy nature. So, and it consists of electric field as well as magnetic field. So that is why it is called as electromagnetic wave. And how does it look? Okay, so here after a lot of study and research, you could see the diagram the scientists proposed here. Okay, they said that if this is x-axis, if this is y-axis, and this is z-axis, if electric fields are oscillating, okay, if electric field is moving in z-axis, then the magnetic field will always move perpendicular to y-axis. Okay, the magnetic field will always move perpendicular to y-axis. So there's an angle of 90-degree between electric field and magnetic field. So they are perpendicular to each other. They are perpendicular to each other. And what happens is, we know that, right, in the last chapter, whenever electric field changes, magnetic field produces, and whenever magnetic field changes, electric field is produced, right? So this is a bit somewhat idea what we got in the last chapter. Whenever current is changing, we get magnetic field. Whenever magnetic field is changing, we get current, right? Current is nothing but electric field, right? So this is what we have studied. And if you can notice, let me show a different diagram here, students. So this is how they propagate. Okay, so this is how it looks. The blue line is electric field, the red line is magnetic field. If you notice, their magnitude is always same at all the instant. Their magnitude is always same. Okay, for example, see, the electric field is oscillating in y-axis. For this example, in the second diagram, electric field is oscillating along y-axis in blue color. And what is happening to the magnetic field? The magnetic field is oscillating along the z-axis, right? And change in electric field gives out magnetic field, and change in magnetic field gives out electric field. Okay, that is what happens, and they have same magnitude. If he is 1 centimeter long, B is also 1 centimeter long. If he is having no length, E also doesn't have, or B also doesn't have no length. Okay, they are always equal. The amplitude of electric field and magnetic field are always same in an electromagnetic radiation. Cool, right? So we have learned two things till now. The first thing what we have learned is uh, how do we get the radiation? So by accelerating a charge, you get radiation. And how does it look? Electric field and magnetic are perpendicular to each other, and changing electric field gives it magnetic field, changing magnetic field gives it electric field. Okay, so am I clear? Click on yes, guys, if I'm clear with this. Okay, quick, come on, guys. If you have any doubts, you can let me know. If you don't have any doubts, I'll move on to next part of the chapter. Okay, click on yes or no, quick. Yep. Okay. Yeah. So will I continue classes during the exams? So what do you think? Should we continue? You tell me. How will it be comfortable? Okay. Yeah. So two things. Sorry for repeating it again. Whenever charges accelerate, charges at rest gives out electric field. Charge at constant velocity gives electric field, magnetic field. Charge accelerating gives electric field, magnetic field, as well as radiation. So now in this chapter, we're going to talk about this radiation, which is given by accelerating charges. And when I check for the diagram, they have electric field perpendicular to magnetic field. E is always perpendicular to magnetic. They'll be always having 90-degree, and then magnitudes are same always. Okay. So then, okay. So, okay, sir. Then, okay, I understand that there is electric field and magnetic field. Then how many kinds of radiations are there, you might ask, right? So there are different kinds of radiation. There's like huge number of different types of radiation. So what happens is, I'm showing you the diagram here. Okay. So I'm pretty sure you know about this, and the total radiation given in one diagram is called a spectrum. Okay, electromagnetic spectrum. So what is an electromagnetic spectrum? A spectrum gives me the idea of all different kinds of radiation. For example, see here in this diagram, let me start with the wavelength. So we all know what wavelength is, right? So what is wavelength? So the length of a single wave is called as wavelength. For example, if I write one wave in this particular way in this diagram, this has a very big wavelength. So this is the wavelength lambda, right? And if I write one more wave in this particular in this way, so this wave has very less wavelength because it's very small. So this has a very smaller wavelength, and this has very longer wavelength, right? So the length of a wave is called as wavelength. And what is frequency? Number of waves per second. For example, see this shorter yellow one. So this can give me in 1 second, this can give me 2, 3, 4 number of waves. So this has high frequency. But the old one will be having lots of waves. I mean, it will be having only one wave, right? So that's about frequency, and it's the concept which I already studied in high school and 11th, I suppose, right? So let me come back to here, and let me start with one kind of radiation called radio waves. Okay, radio waves. So what's the radio waves? So radio waves is usually we use it for communication, right? And you might have seen like All India Radio, they do communicate. The cricket commentary in the olden days, the programs in All India Radio, and even satellite communication uses radio waves, and they have very large wavelength. They're not small waves, they're very, very huge waves. Okay. So they have wavelength up to at least a kilometer. Like they can have a wavelength up to from a meter to a kilometer. Okay, they can be a short wavelength up to a meter, and they can extend up to a kilometer, tens of kilometers also. All right. And next, after radio waves, if I reduce the wavelength, if you can notice here, so the radio waves is very large here. Now I'm reducing the wavelength. Okay, when I reduce the wavelength, I get something called as microwaves. So microwaves are the electromagnetic radiation which have wavelength about a centimeter. Okay, if the wave is very small as a centimeter, the wavelength is small as a centimeter, then they're called as microwaves. Okay, and where do we use microwaves? We use microwaves for cooking. Again, we use it for communication also. Okay, we'll see the uses at the end of the class. Okay, and if I again reduce the wavelength, and if the wavelength becomes much smaller and smaller, okay, up to at least near 10 micrometer or 10 raised to minus 5 meter, I get something called as infrared waves. Okay, so what are infrared waves? Okay, if you know anything about waves, you can always text me in the chat box. Okay, YouTube guys and Zoom guys, you could text me in the chat box. So infrared waves are the waves which we usually use it for heating an object. Okay, and any object which has a slightly higher temperature will always emit infrared radiation. So they are a symbol of heat. Okay, they're a symbol of heat. Every object which is hot emits radiation, and most probably it will emit infrared radiation. Okay, and if I again reduce the wavelength, And if I make the wavelength very much smaller, up to a micrometer, then I come to a spectrum called visible light rays. That Vibgayar color, right? Violet, indigo, blue, green, red will be in this here only. So what happens here? If you notice here, at the end of infrared, I start with color red, then visible light ray comes here. After visible light ray, I get ultraviolet light ray, ultraviolet, right? So this is how it looks. Our human eye cannot see radio waves, it cannot see microwaves, so they're not visible. They cannot see infrared, so they're also not visible. They can see red light, so this is visible here. Okay, then after red, yellow, green, blue, everything it can see, right? Then up to violet it can go here. After violet, again ultraviolet starts, and again after ultraviolet we can't see ultraviolet color, so they're not visible. So they're completely not visible. They're completely, uh, invisible to us. So in between this spectrum is what we can see. Okay, so after visible we get ultraviolet light ray, and again they have very short wavelength, high frequency. Okay, they have again very short wavelength, and these are responsible for, you know uh, these are very dangerous. Okay, they can cause cancer if you have prolonged exposure to ultraviolet light rays also. Okay, and again, if you increase the frequency or reduce the wavelength, if the wavelength becomes shorter and shorter, you get something called as X-ray. Okay, X-ray we use it for medical purpose. If you remember, we use this for medical purpose, right? So and they have very short. See, the wavelength of these waves are up to an Armstrong. 10 raised to minus 10 is an Armstrong, right? So they have very short wavelength. And again, if I reduce the wavelength and make it very high frequency, I get something called as gamma rays. So these are very strong. Radio waves are weak, and microwaves are stronger than radio waves. Infrared is much stronger. Ultraviolet is much more. X-ray is much more stronger, and gamma rays are the strongest of all the waves. Okay, they are very much strong. Okay, and they have very short wavelength and high frequency, because if you know the basic property which is studied in high school, velocity is equal to frequency into lambda. Okay, therefore I can say that frequency is 1 by lambda or v by lambda, right? So frequency and wavelength are inversely proportional. For example, radio waves, which has very large wavelength, has a short frequency. It has only 10 raised to 4 frequency. Well, now I'm decreasing the wavelength. See, the frequency is increasing. Becomes the frequency of microwaves 10 raised to 8. And come back to gamma rays here. Gamma rays are the shortest wavelength object radiation, but they have the highest frequency. So you can see the wavelength is reducing as I go towards right, but frequency is increasing as I go towards right, because wavelength and frequency are inversely proportional to each other. Cool, right? And of course, if you remember Einstein's formula or Planck's formula, E is equal to h nu, E is equal to h frequency. Planck's constant h. So this says that the frequency of radiation depends on the energy, right? Energy depends on the frequency. If the frequency is more, then the energy is also very high, right? So this is the different kinds of X-ray, electromagnetic radiation. What do we see? Okay, cool, right? So am I clear, guys? So am I clear with the varieties here? So are we clear? And you can see the dimensions of X-rays. So radio waves are as big as building. Gamma rays are as short as an atom. Okay. So that's you can also use this. If you can come back to my class on the PDF, you can read it again. You can note them down. Not a problem. Okay. Cool. Right. So am I clear, guys? If I'm clear, click on yes. YouTube guys, am I clear? Zoom guys, am I clear? Oh, okay. Cool then. Okay. Yeah. Okay. Yeah. Moving ahead. Okay. So So these are the different kinds of radiation. Remember them, and together, if I write them in the same diagram, they are called a spectrum, electromagnetic spectrum. Okay, yeah. And so I already told you what are these made up of. So let's see some properties of electromagnetic radiation. Okay, what are the properties? So we have learned they have some particular wavelength, they have some particular frequency, they do have some energy also. So let us try to find some other properties. Okay, so what are the properties of electromagnetic radiation? So the radiations are made up of oscillating electric field and magnetic field perpendicular to each other. Very simple. So they are made up of electric field and magnetic field oscillating with respect to each other. Okay. And how do they travel? They always travel at the speed of light, 3 into 10 raised to 8 meter per second. So they're very fast. Okay. And they do travel at this velocity. Always, always. Okay. In vacuum, remember that. In vacuum. In medium, it can change. For example, in glass, they will travel a bit slower. Okay. And in diamond, they again travels much slower. Okay. Depends on the medium. But in vacuum, they can travel at speed of 3 into 10 raised to 8 meter per second or 3 lakh kilometer per second. Okay, so what are these types of waves? If I remember in the 11th standard, there are two kinds of wave. One is called the transverse wave, other is called the longitudinal wave. An alternate compression, rarefaction, like sound waves, if you remember, right? The basic concepts, the basic kinds of waves. So here we can say that the light waves are transverse wave. They are transverse wave, like they are oscillating like this continuously. Transverse waves. Okay, cool. And as I move on to the higher, the next part, governed by. So what, like for particles we use Newton's law, for electrostatics we use Coulomb's law, for quantum mechanics we use Schrodinger equation, for highest speed we use relativity. And what laws do we use to understand radiation? We use Maxwell's laws of electromagnetic radiation. Maxwell's laws of electromagnetic radiation. So Maxwell, James Clerk Maxwell was a very great scientist, and he do gave a laws. That's correct, Navin. Yeah. So he gave Maxwell's law. He gave actually four. I mean, they are not his law, but he collected laws from different people and explained the whole radiation completely. Okay, and they are called Maxwell's law of electromagnetic radiation. They explain the whole mechanism of EMFs are given by Maxwell. Okay, and how do they interact? Okay, they have all kinds of interaction. They have reflection. Of course, the electromagnetic waves undergo reflection. They undergo refraction. They undergo interference. Okay, interference we'll see in wave optics. Okay, so they undergo interference. They undergo photoelectric effect. They undergo diffraction also. So we are going to see diffraction interference in the upcoming chapter of wave optics, and photoelectric effect in modern optics. Okay, we'll see them. Reflection and refraction, we'll see them in ray optics. Cool. So these are the basic properties. Cool, right? Am I clear, guys? Am I clear with this? They undergo like a lot of interaction. Almost all the interaction what a normal wave undergoes, electromagnetic wave also undergoes the same interaction. Okay, photoelectric effect. Acha, so okay, bro. So what's happening here is there is something called as a dual nature. Okay, see, okay, what happens is electromagnetic radiation. Okay, the a packet of X-ray. Okay, a packet of just a small quantum of X-ray can cause photoelectric effect. Okay, usually when I come to photon, right, I'm not talking about photon here, right? I'm just talking about radiation. But usually photon can behave as wave as well as particle also. They have both the properties. So we call it as dual nature. Okay, there's a separate chapter on this. We'll come back to dual nature. We can see how a particle undergo, how light can be thought as a wave and how light can be thought as a particle also. We'll see both of it. Okay, yeah, cool, bro. Okay, so and okay, so I'll come back to the propagation. Propagation. So how do they move from one point to one point? If I want to throw an object, I have to put some force. They'll travel, right? They have some projectile motion or some kind of motion. But how do these waves travel? How they travel from one point to one point? They travel because of oscillating electric field and magnetic field. As I told you here, they're made up of electric field and magnetic field. When electric field changes, magnetic field is created. And when this magnetic field is created, magnetic field changes, electric field is created. So that is how they propagate. Okay, and propagate, it's a very complex phenomenon of propagation, but we have to just remember these things. What I'm trying to tell you, we'll understand that when we go to Maxwell's equation, but in a better way. Okay, and the what is the velocity of radiation? As I told you, that they travel with the velocity of 3 into 10 raised to 8 meter per second, and it is given by the formula C is equal to F lambda. Okay, so remember this formula where C is called the speed of light. Speed of light, it's constant. It's always constant in a medium. And F is called frequency of light, frequency of wave, and lambda is called as wavelength. So once if you know the wavelength, you can calculate the frequency. If you know frequency, you can know wavelength. They're interchangeable. Okay, so remember that. Right. So, okay, so this is formula which you've already seen for a very long time, but there is one more formula. Okay, there is one more formula. There are many formulas. So I'm writing one more formula, which is velocity c is also given as 1 by root of mu naught epsilon naught. Okay, where c is again the speed of light, and here mu naught is called as uh, permeability, right? Magnetic permeability. Okay, it's a constant value, and epsilon naught is also given by permittivity. Permittivity. Yeah. So what's permittivity? It is 8.86 into 10 raised to minus 5 units. And what is permeability? 4 pi into 10 raised to 7 units. Okay, so plus 7 or minus 7. I have to check it out. I'll let you know. And these are the constants. Yeah, minus. Okay, so both of them are minus. Exactly. So if you take these two constant, okay, for example, if you want to verify, put mu naught here, put epsilon naught here, take the square root, divide it. I'm very sure you'll be getting around 3 into 10 raised to 8 meter per second. So this was derived by again using Maxwell's equation. Okay, so this is very important formula, very important formula. Okay, you might get a direct question. You might get a direct question on this formula. So remember this. Okay, cool. And the last formula, okay, which is related in terms of electric field and magnetic field. As I already told you, the force of electric field and force of magnetic field is same in electromagnetic relation. Electric force is given as charge into electric field. Magnetic force is given as charge into velocity of the particle and into magnetic field B. So if I divide Q and Q, they cancel out, and I get E is equal to CB, or C is equal to B by E. B by E. Okay, and to be more accurate, the most maximum amplitude. Electric field and magnetic field is always changing, right? So we have to consider the highest amplitude. Okay, B naught and epsilon naught. So this is, am I right? Oh, sorry. C is equal to E naught by B naught. Okay, yeah, yeah, just corrected. It becomes C naught by B naught. So these are the three formulas which are very important, and you are going to need them very high, because in many of the JEE exams, even in advanced exam also, they have asked a direct question on this formula. They'll give you electric field. They'll ask what is the magnetic field of the electromagnetic radiation directly. Okay. The problems in this chapter will be very easy. So try to remember them. Okay. Cool, right? Yeah. So these are the three formulas, guys. Am I clear? If you're clear, let me know. Okay. So then I'll move on. Okay. So three formulas. They should be very clear. Yeah. Zoom guys, YouTube guys. Any doubts? Okay, so we could derive them, of course, we could derive them, but not through our regular classical knowledge. We have to derive them only using Maxwell's equation. Okay, I'll tell you what Maxwell's equations are also. Okay, click on yes if you're clear. Okay, so I'll write down the three expressions. C is equal to F lambda. So this gives me the information between frequency and wavelength, and C is equal to root of 1 by mu naught epsilon naught. Okay, I can bring the square root upper side also, not a problem, because one square root is one only, right? So this is the velocity of light with respect to permeability and permittivity. Those two are constant, and what happens next? C is equal to E naught by B naught. E naught by B naught. So this is from the Lorentz force. If charge into electric field is equal to charge into speed into B, I can cancel these two, and I can get E by B is equal to C, speed of light. Okay, so I can derive this formula here also and here also. Okay. So I told you, right, one thing, like the speed of radiation is different in different medium. In vacuum, it is 3 to 10 raised to 8. So if I put mu naught and epsilon naught, I get 3 to 10 raised to 8. But instead of vacuum, if this permeability and permittivity depends on the medium, for glass they are different. So for when they're different for glass, C also changes. So this gives me just information about frequency and wavelength. So this gives me why speed of light changes from medium to medium. In every medium, the speed of light is different. Why it is different, I can understand from this formula. Okay, and relation between electric field and magnetic field will be given by this formula. Cool, right? Am I clear, guys? Then, so you remember these three formulas, and it's sufficient to move ahead. Okay, yeah, cool then. Okay, so if you have any doubt, again you can text me. Am I clear now for everybody? Yeah. So if you again have some more doubt, you can again text me back. Not a problem. Okay. Yeah. So no, bro. Nah, the derivation is not important. Just remember this formula. Just write them down, remember them. Okay. Yeah. So there is no derivation of this formula. If you remember them, that's completely fine. C is equal to f lambda, c square is equal to 1 by mu naught epsilon naught, and c is equal to e by b. That's all. Nothing much. Okay. It's like don't think it's like we are trying to by heart it, but the thing is we couldn't prove it with our knowledge, primitive knowledge, right? We couldn't prove it. But if we understand Maxwell's equation very well, we can prove them. Not a problem. Okay, cool. Okay, so coming back to the concept of energy. Okay, so we saw here in this electromagnetic radiation the different kinds of radiations, right? And we'll just concentrate on this visible part for some time. Okay, so I'll ask you a question, guys. Which part here is very strong? Is the red light strong, or the yellow light stronger, or the blue light stronger? Which one, Prashant? Which one do you want to know again, bro? So which is stronger? Is the violet is stronger, or the red is stronger, or the yellow is stronger? Which do you think is very strong? Achha. So, Prashant, okay, bro. Do one thing. You note the formulas down. Okay, and we're going to use them in the upcoming class. Okay, there is not much to learn here. Okay, you didn't learn anything from this slide. I just stated formulas. I stated c is equal to f lambda. I stated c is equal to 1 by root of mu naught epsilon naught, and I told it c is equal to e by b. That's all. Okay, there is no concepts based on this. This formula gives me information about frequency and wavelength. This formula gives why speed of light changes when mu and epsilon naught are changed. Okay, because speed of light is different in different medium. This depends on medium. Okay, and this gives me like information between electric field and magnetic field. Just note them down. We're going to use in higher concepts. Okay, yeah. Okay, so guys, come on now. Tell me which is stronger here. There is the red stronger, or is the green stronger, or is the blue stronger? Okay. Achha, so many of you said it is red and few said it is blue. Okay. So we have to use a formula given by Max Planck. So Max Planck was a scientist during Einstein's time, and he gave us a formula, okay, which was energy of a photon or energy of a radiation is proportional to its frequency is equal to h nu or is equal to hf. Okay, he said that which radiation of higher frequency they have higher energy. That's what I told you, right? Radio waves are though very long, they have less energy, and gamma ray though they have short wavelength, higher frequency, they are very strong. So gamma ray are stronger than radio waves. Similarly, you can notice from this diagram, the wavelength of red is very large. See, one wave is this large, and one wave of green is this small, and blue is much smaller. So since wavelength is c is inversely proportional, c is equal to f lambda, and frequency is proportional to lambda, inversely proportional to lambda. As lambda decreases, frequency increases. So frequency of blue is greater. Okay, so let me note it down here. Frequency of this is not a good color. Uh, so frequency of blue is greater than frequency of green, than frequency of red. Right? You can notice because, for example, imagine just in 1 second the waves start from here and all the waves end in 1 second. How many waves of red do I have? I have one and a half red waves. How many waves of green have? I almost have uh, two waves, two of green waves. And how many waves of blue have? I have two and a half blue waves. So the frequency of blue wave is very, very strong. The blue have a lot of frequency. Therefore, energy of blue is greater than energy of green, which is greater than energy of red. Okay, so blue has a lot of higher energy. And if I go back to my concept here, this concept you can notice here, right? As the frequency increases from this side to this side, energy also increases. So gamma rays are very, very strong than X-ray. Okay. Then X-rays are stronger than ultraviolet rays. Ultraviolet are stronger than, I'm sorry, it's the reverse. Okay. Gamma rays has a very strongest wave. X-rays lightly less stronger. Ultraviolet is slightly less stronger. Visible is not that strong. Infrared is a bit weak. Micro is very, very weak. Radio is the weakest. Okay. So as you go towards right, frequency increases. See, frequency increases as you go towards right, therefore energy also increases. Right? Yeah. Okay. So that's about in here, and that is one of the reason why we use red light for indicating signals. For signals, why we use red light is because they have less amount of energy, they won't get dissipated very fast. The dissipation is the scattering is less. So do you guys remember CV Raman, Sir CV Raman? And he also worked on scattering, and he gave us one formula, which is lambda. Okay, the scattering ability is inversely proportional to lambda raised to 4. If lambda is high, scattering is less. Okay, if lambda is small, scattering is high. For example, notice here, the red has very big lambda, so scattering is less. Whereas the green has lesser wavelength, so scattering is more. And where the red has very small, the blue has very small wavelength, so scattering is very high compared to red. That is why we use red light, because when we use red light in traffic signals and we will use red light in our vehicle, they won't get scattered. They stay there. They can travel for longer distances. Okay, they won't get distracted or diffracted. They stay there. Like, I mean, this is not so important. This is not there for your syllabus. Okay, don't worry. But very simple. So electric energy is given by E is equal to H into frequency. And if frequency is high, energy is high. Red light has lower frequency, so lower energy. Blue light has higher frequency, so higher energy. Simple. Oh. Am I clear, guys? Am I clear with this concept? Click on yes if I'm clear. YouTube guys, am I clear? I'm sorry, I'm unable to respond to YouTube chat very frequently because I don't have access to YouTube here. Okay, so cool. Many of you give the right answer. Good guys, awesome. Okay, keep it up. Good. Oh, cool then. Shall I move ahead to the new concept? Yeah. So same for velocity, we had three formulas, right? And even for energy also we have multiple formulas here. Okay. So the energy, the same formula. I'm going to write the same formula given by Max Planck. The total energy of a radiation is given by H into nu or HF. Both of them are same. Nu and frequency are same. They're different alphabets. That's all. Okay. So it depends on frequency, higher energy, and H is Planck's constant, where H is equal to 6.634 into 10 raised to minus 34 joules second. It's a very small number, very small. 10 raised to minus 34. Imagine you have to just write 34 decimals before you write 663, right? That's a very small number. That is why energy have a bit of less radiation. Like for example, if I take a hair dryer which we use to dry our hairs after taking bath. And if I switch the hair dryer on, then if I keep a ball, the plastic ball can float. But if I take a torch, and if I keep the plastic ball on the light, it will not float because the light energy is very low. It has very low energy. Okay. But if I take like gamma rays or X-rays example, they're really strong. Okay. Yeah. And okay, so where does this energy come from? For example, I told you that electric field is just made up, radiation is just made up of magnetic field and electric field. So where does energy come from? This energy comes from electric field and magnetic field. So some part of this energy is stored as electric field and some part of this energy is stored as magnetic field. Okay, so let me finalize the slide here. Energy is equal to H nu or HF, and H is equal to 6.634 into 10 raised to minus 34 joule second. So this is very small. Energy is very small because it's 10 raised to minus 34 is a very small number. Okay, and how does this energy comes to radiation? So this energy comes to radiation in the form of electric field and magnetic field. Okay, how do I get? I'll write the formulas and I'll derive it in the next slide. So energy density, okay, energy per unit volume. So total energy per unit volume is called as energy density U, and energy density of electric field is given by half epsilon naught E square. Okay, and energy density of magnetic field, okay, is given by half B square by mu naught. Half B square by mu naught. Okay, so this is amplitude square, and this is amplitude square by mu naught. So this is magnet electric field energy. Okay, this E is energy of electric field, and this B is energy of magnetic field. I'll derive this formula. Don't worry. Okay. So only when I derive this formula, I'll come back to the slides again. So just let me write E is equal to H nu. That's all. Okay. So how is electric energy? How is energy stored in electric field? Okay. So for that, I'll take example of capacitor. If you remember capacitor, guys, in capacitor, electric field exists right in between two plates. between these two plates. Imagine this is positively charged, imagine this is negatively charged. So electric field moves from positive to negative end, and electric field is stored in a capacitor. Capacitor is a battery. Battery store energy, and how does it store? The capacitor stores energy in the form of electric field. Okay, it stores in the form of electric field. A regular battery for a EMF stores energy in the form of chemical, but capacitor stores energy in the form of electric field. Okay, so let me try to derive this. I know, I know we have derived this formula already, which is the energy of a capacitor is half CV square. You remember this, where U is the total energy of the capacitor, half is constant, C is capacitance, V is potential difference. So this is the total energy of a capacitor, which we already derived in the capacitor chapter. And we need to know two formulas, which is C is equal to epsilon naught A by D, okay, the geometrical property of capacitance, and electric field is equal to potential by distance. Potential by distance, or you can modify this and write potential is equal to electric field into distance. V is equal to E into D, right? I'm just cross multiplying. I'm sending the D to the left hand side. So then I get V is equal to ED. That's all, guys. So you take these two formulas and combine now. Okay. So instead of half, right, as it is, no problem. U, capital U, total energy. U is capital U is total energy. Keep it as it is. What is C? C is epsilon naught A by D, capacitance. I'm writing the capacitance formula. And what is potential square? Potential square is electric square into D square. Okay, I'm using this formula here. Okay, so now we'll see what happens. So 1D and 1D cancels out completely fine. So therefore, U is equal to what I'm left with, half epsilon naught as it is, area as it is. Okay, so let me write E square first. Electric field square into area and distance. So can you tell me, Chris, what is area into distance? Area into distance is volume, right? For x square into distance is x cube, right? Or pi r square into distance is again, you get volume. So this is nothing but volume. Okay, so this A into D is volume. You bring the volume down to the denominator, you get the formula. Total energy by volume is equal to half epsilon naught E square, and this is called as small u, energy density. This is called as small u, energy density. So this much amount of energy is stored in capacitor in the form of electric field. Very simple derivation, right? I'll do it again, not a problem. Okay, so I'm just giving an idea here. So yeah, I remember this. I'm taking a capacitor. In capacitor, energy is always stored in the form of electric field. The field travels from positive side to negative side, and total energy was given as half CV square, half CV square, right? And where C was equal to epsilon naught A by D, this was capacitance, and where V is equal to electric field into distance. Okay, using these two formula, I'm going to substitute them half as it is. What is C? C is epsilon naught A by D. Not a problem, very simple, write it down. What is potential? Potential is E square into D square, because we have a potential square here. I'll square whole side here. I get E square D square. DD cancel ho jayega. And I'm just left with half of epsilon naught E square, area as it is, distance as it is. Area into distance can be written as volume. Okay, so this whole term will be written as volume. So how I modify this formula is very simple now. I'll write half epsilon naught E square as it is, and right side is equal to total energy, capital U. Okay, and this I'm bringing it to the denominator here, so divided by volume, and this is equal to energy density small u. So this is the energy density of an electric field, not just in electromagnetic radiation, but everywhere. Okay, if this is the electric field, then you can say that acha, this much amount of energy density is always there. This much amount of energy density is always there in electric field. You can say this. Okay. Cool, right? Again, derivation, it's not there for your syllabus. Just I derived it here. But remember, okay, it's very easy and it's good to remember. Okay, cool. So let me tell you then, what is the energy density of magnetic field? Acha, if this is energy density of electric field, similarly, an inductor, right? We learned about inductor very broadly, right, in the last class. So in inductor, again, energy density is stored, but it is stored in the form of magnetic field, because we know that inside the solenoid there is no electric field, rather than there is magnetic field, right? So your energy is stored in terms of magnetic field. We can modify this to magnetic field also. So let me write energy density, energy by volume. Energy density is called energy by volume, half epsilon naught E square, half epsilon naught E square. Okay, by the third formula of electric velocity, C is equal to electric field by magnetic field. I know this formula. Therefore, electric field is equal to B into C. I'll use this formula. Okay, I'll use this formula. Instead of E square, I'll write B square C square. Very simple. Okay, half as it is, epsilon naught as it is. Instead of E square, I'm writing it as B square C square. Very simple. Okay, see, now I got my energy density in terms of magnetic field, but one small substitution is, instead of C square, if you remember guys, we know that C is equal to 1 by root of mu naught epsilon naught, right? So what I do here is, I'll just square it. If I take C square, square and square root cancel out, I get C square is equal to 1 by mu naught epsilon naught. So epsilon naught as it is, B square as it is, no change. C is equal to 1 by root of mu naught epsilon naught, and squaring it just gives me mu naught and epsilon naught. One epsilon naught cancelled out, and energy density of magnetic field U is equal to half B square divided by mu naught. So this is the energy density of magnetic field. Am I clear? Okay, this is the most simplest formula. So what I did is, first I derive the formula for electric field, then instead of E, I'll substitute it as BC. Okay, okay, and a C is written as mu naught epsilon naught. Okay, that's all. 1 by mu naught epsilon naught. If you substitute it, you'll get the formula also. So let me come back here and I'll write the formula. So this is the total energy of our radiation, and energy density in form of electric field is given as U is equal to half epsilon naught E square, and energy density of magnetic field is given as U is equal to half B square by mu naught, where E and B are maximum electric field. Okay, where these are maximum amplitude of electric field and magnetic field. Cool, right? And energy density. So what is energy density? Energy density is energy by volume, like mass density. What is mass density? Mass density is mass by volume. Energy density is energy by volume. Cool. Am I clear, guys? If I'm clear, click on yes. And if you have any doubts, let me know. Okay. So totally we have 6 formulas to remember now. 3 formulas from velocity, 3 formulas from energy. Okay. Am I clear, guys? So if you have any doubts, you can text me right now. I'll respond to it. Okay. Yeah. Okay. No doubts, right? Okay, cool then. Good. Very good, guys. So this this is like almost like most of the chapter is already over, right? So a very small part is remaining, which is displacement current. Okay, which is very important again, and Maxwell's equation. So before going to those two, because the probability of you getting question from those two is not good, but before going to that, let us solve some question. Okay, because like just giving you formulas and asking them to remember is meaningless if I don't solve any problem. Okay, so let us solve some question. Okay, so here the question here is the electric field of an electromagnetic wave. So remember, whenever there comes a word wave, you can write wave as y is equal to y naught sine omega t minus kx. So this is the wave equation what you learned in the last class, right? In the 11th standard. So where y is called the displacement, y naught is called the maximum amplitude, omega is angular frequency, t is time, k is wave number, x is displacement in x direction, right? So this is wave equation which is studied in 11. So whenever you see wave, you can use this kind of equation. Okay, and here electric field can also be expressed in the same way. Electric field E is equal to E naught sine omega t minus kx, and magnetic field is also can be written as B is equal to B naught sine omega t. Instead of kx, I'll write ky, because the electric field and magnetic field has to be perpendicular, right? So if there is one is an x-axis, other should be in y-axis or z-axis. They should be perpendicular to each other. Okay. Okay. Cool. So this is over. And here they have expressed in this question. They're given that in certain space there is an electric field which is given by the equation. On this color, by an equation E is equal to 50 per Newton sine omega t minus x by c. Okay, this is a different form of wave equation, not a problem. So they are given this is the wave equation for electric field. Okay, and they're asking find the energy contained. They're not asking for energy density, they're asking for total energy. Find the energy contained in a cylinder of cross-sectional area 10 centimeter square and length 50 centimeter. Okay, and what's happening is they have a cylinder. Okay, they have a cylinder which is an area of 50, not 50, yeah, 10 centimeter square. So they have an area of 10 centimeter square, and the length is 50 centimeter. And what are they doing? They're sending electric field here through this cylinder. And in this cylinder, they're asking me how much energy is stored. What is the total energy stored due to this electric field? Again, it's very simple because I know that energy density small u is energy by volume. If I want total energy, what I do? If I want total energy u is equal to what? Small energy density into volume. So I'll use this formula and I'll get the answer. So what is the energy density of electric field? Half epsilon naught E square into what is the volume? Volume is area into the distance, area into length. So this is the formula. Okay. And if I substitute the values directly, I'll get the answer. Okay. So nothing much here. If I substitute half as it is, and if I take epsilon naught is equal to 8.86 into 10 raised to minus 5, and electric field V, what is electric field? Yes, electric field is 50. I have to take the maximum amplitude, so it becomes 50 square. So what is the area? Area here is 10 centimeter square. 10 centimeter square. And what is distance? Distance is 50 centimeter. Okay, see just all numbers. Half into 8.86 into 1.5 into 50 square into 10 centimeter square into 50 centimeter. If we just multiply this, we get the answer, and it will be any one of this option. Okay, and always remember, keep all of them in SI unit. If it is centimeter square, convert it to meter square. If it is centimeter, convert it to meter. Okay, cool, right? So I'll tell you again. So pay attention. So what's happening here in this question is they have a cylinder. In this question, they have a cylinder. The cylinder has a cross-sectional area of 10 centimeter square, and the length of the cylinder is 50 centimeter. Okay, and they're asking how much energy is stored if electric field is passing inside the cylinder in the form of electric field. So what do I do is very simple. Energy density is equal to total energy U by volume. Okay, so this is total energy by volume. And this is called energy density. If you want total energy, because they're asking what is the energy contained, so total energy U is equal to energy density into volume. Okay, I'll just multiply this here, so I get total energy U, capital U, right? So what is total energy? Capital U, that is equal to energy density into volume. So what is the energy density of electric field? Half epsilon E square is the energy density of electric field. Okay, and into what is the volume of a cylinder? Area into distance is the volume of a cylinder. Okay, bas. Okay, just substitute the values. Okay, half is constant, so I'll rate it as 0.5. And what is epsilon naught? Epsilon naught is 8.86 into 10 raised to minus 5 or 10 raised to minus 12. I'm not sure about this constant. Okay, check in the internet, guys, or check it in the textbook. Okay, I think it's minus 12, I suppose. Um, yeah, but anyhow, check about this constant. Okay, usually it will be given in the question. If it is not mentioned, don't worry, it will be given in the question. And okay, area is given. Area is very simple. Okay, so area is 50 centimeter square. So centimeter square is 10 raised to minus 4. Completely fine. What is area? Area is 50 centimeter. 50 centimeter is 50 into 10 raised to minus 2 meter. Completely fine. So what should I put for electric field? So they have given this equation here. Pay very careful attention. The electric field is equal to 50 per Newton sin omega t. Okay, if I compare this with my regular equation, E is equal to E naught sin omega t minus kx. They are given here E is equal to 50 sin omega t minus kx. So therefore E naught is equal to 50. So instead of E square, you multiply it by 50 square. Bas. Okay. Okay, am I clear, guys? So just if you multiply this expression, you get the answer, and it will be any one of this option. Okay. Cool, right? I leave the calculation to you. Okay. I hope you can do that. Cool. Yeah. So see, these are previous year questions. These are not the random questions. These are previous year questions. So these are very simple calculations. Just you need to remember the concept. Okay. Okay. So can I solve next question then? I leave this to you to solve. Multiply all of this and you'll get any one of this answer. Okay. Achha, this is 5 itself, I suppose. Yeah. Okay. Cool. So then moving on to next question, guys. So what's going to happen in next question? A plain electromagnetic wave of frequency. So they're given the frequency of a wave travels in a space along x direction, completely fine. At a particular space and time, the electric field is equal to 6.3 J. So J is it's moving in y-axis. Electric field is moving in y-axis. Okay. So the value of magnetic field will be, okay, so they are given all of them in k direction. So electric field was moving in x direction, so they are moving k direction. So not a problem. It's completely fine. Okay, so it's very simple. Let me write it down. So they are given that there is an electromagnetic wave of frequency 25 megahertz. Okay, completely fine. Okay, and it is traveling in x direction. Okay, and the electric field is oscillating, and it has a magnitude of 6.3 volt per meter, and it is in j cap, j direction. So it is in y direction. Therefore magnetic field will be in z direction, right? X y ho gaya, so z mein magnetic field hoga, right? uh, and what will be the, they're asking what is the magnitude of magnetic field. Okay, I leave up to you. So I launch the poll. Using the formulas which you have learned, you can solve this question. Okay, so what are the formulas we have learned? We have learned c is equal to f lambda, c is equal to e by b, right? And c is equal to root of mu naught by epsilon naught, and d is equal to h nu, u is equal to half epsilon naught e square, and u is equal to half b square by mu naught. So these are the only formulas which you have learned till now. I have to use one of this formula, from which if I use electric field, I can get magnetic field. Use such formula from this slide and solve and tell me what is the magnetic field. They very clearly they are given. The electric field is 6.3. Can you tell me what's the magnetic field? Or which formula should I use? Any idea? So you could notice, if you notice the second formula, guys, here, very simple, right? C is constant, very simple. So C to pata hai, 3 into 10 raised to 8. Electric field is given. Okay, only thing is I need to find magnetic field B. Bas, ho gaya. Okay. So therefore, what do I do is magnetic field B, I'll send B to the numerator and C to the denominator is equal to E by C. Okay, yeah. What is electric field? Electric field is how much? Electric field is 6.3 volt per meter given the question, divided by what is speed of light? 3 into 10 raised to 8. Okay, so 3 ones are 3 twos are 3 ones are 0.1s are. So 2.1, 10 raised to 8 goes to numerator, becomes 10 raised to minus 8. Okay, check which option do we have. We have it in option C. Right, C is 2.1 into 10 raised to minus 8 kt. What is k here? That means it is moving in z direction. I j k. This is I, this is j, this is k. So it's moving in z direction. Okay. So I'll tell you one more shortcut trick to remember the direction of wave. Okay, that is direction of E cross. E cross B is a direction of wave. For example, imagine if this electric field is oscillating in x direction. Okay, if electric field is oscillating in x direction, and if this uh, magnetic field is oscillating in y direction, you can easily say that the wave is coming towards you. Okay, you take your right hand, keep your fingers towards x, turn them toward y, you get thumb pointed towards you. Use right hand screw rule for cross product. I hope you remember this concept. Okay, first year, first chapter concept. So cross product, x cross y gives the direction of wave. So that means wave is coming towards you. Okay, or if you say that, electric field uh, is electric field is oscillating towards the north side, and magnetic field is oscillating towards the right side. If you take your right hand, do E cross B. You take your hand, fingers towards E, then turn it towards B. The thumb is going into the board. So this is the direction of magnetic field. They are going into the board. Okay, the wave is traveling in this direction. Cool, right? Yeah. So E cross B gives the direction of wave. So let me write the down point here. Okay, remember this. The direction of magnetic field, so direction of electromagnetic wave is given by, okay, E cross B. E cross B gives the direction of wave. The thumb. When you cross E and B, the thumb direction will give you the direction of wave. Cool, right? Okay. Am I clear with this concept, guys? So very simple formula. This was asking previous question. Just use this formula. B is equal to E by C. Ho jayega bas. Okay. Cool, right? Okay. So let me give you such kind of question, similar question. A plain electromagnetic wave propagating in space as an electric field of 9 to 10 raised to 3 volt, 9 to 10 raised to 3 volt per meter. Then what is the amplitude of magnetic field? So I'll be relaunching the poll again. So let me see how many of you will answer very quick. Okay. So YouTube guys, am I clear? Any issues? That's correct. Lakshmi and Madhavi, good. Okay, so we'll solve some question on this concept which have frequently appeared in previous year, and later on we'll move on to the displacement current and Maxwell's equation. Okay, quick answers come on 30 seconds done. I'll give you 30 more seconds and I'll end the poll because it's a very simple question. Okay, so what's the idea here? They have given that there's electromagnetic wave and it has an electric field amplitude of 9 into 10 raised to 3, and they're asking what is the magnitude of magnetic field. Okay, since it's an electromagnetic wave, it will travel at speed of light c, and I know that E is equal to CB, right? Because if you don't remember this formula, remember QV is equal to QVB, QQ cancel ho jayega, you are left with E is equal to CB. Therefore, B is equal to E by C. Okay, E is equal to C by C. So what is electric field? Electric field is given as 9 into 10 raised to 3. Okay, fine. What is speed of light? 3 into 10 raised to 8. You solve this, you get the answer. Okay, so 3 ones are 3 threes are. So already most of the options are out, right? So option B is out, option A is out. I have to just confirm option C or D. Okay, so next you divide this. 10 raised to 3, 10 raised to 3 cancels out, and you're left with 10 raised to 5. When 10 raised to 5 goes to numerator, it becomes 10 raised to minus 5 units, or magnetic field unit is Tesla. Okay, yeah. So therefore the option is D. D is the right answer. Right. So that's it. That's how simple the questions will be coming from this chapter. But you should be very careful and you should remember the formulas there very clearly. Okay. So last question. So what it is, I just use this formula. Okay. B is equal to E by C. Bas. Okay. And the last question for this chapter is the average density of electromagnetic wave. What is the average energy density? So they're asking small u for electromagnetic wave in terms of electric field. So for in terms of electric field, energy density is half epsilon naught E square. Right? Just use this, you'll get the answer. So what is half? Write it down as it is. What is epsilon naught? Epsilon naught is 50 units. So 50 square. 50 square. And what is epsilon naught? What is epsilon naught? Epsilon naught is 8.86 into 10 raised to how much? Minus 5. Right? So let me check in the internet. Is it minus 12 or minus 5? Because I don't want to get you confused. Value of permittivity. Value. It should be given the question, so I'll give it to you. Yeah. It's minus 12. It is minus 12. Okay, 8.86 into 10 raised to minus 12. So what happens is you can solve it here. So when you divide this way to this, you get 4.46. Sorry, 4.43 into 10 raised to minus 12. 50 into 50 is 2500. Right, 20 cancel karo with 10 raised to minus 12. So 20 jayega. Right, I'm left with 4.4 into 25 into 10 raised to minus 10. 4.4 into 10 raised gives me approximately 100. So 100 into 10 raised to minus 10. So 20 cancel out, and again it will be 10 raised to 8. 10 raised to minus 8. So which is the right answer? Achha, option A is the right answer. Okay, so small manipulations. Slightly you can take the approximate value and you can do the answer. It's not a problem. So this is the energy density in that much amount of electromagnetic radiation. So this is how you get the questions, guys. So these are very simple, right? That's correct, Anikita. Good. Okay. Am I clear, guys? Any problem? Any issues till now? So remember those 6 formula which I taught you and remember them very well. Okay. So next we are going to start Maxwell's equations of motion, Maxwell's equation of electromagnetic radiation. So all this law you already seen it. They are not new laws. You have already know all of this law. So the first law I'll be writing is the first Maxwell's equation is called as uh, Gauss law for electric field. Gauss's law for electric field. So do you remember the Gauss law for electric field? Integral of epsilon naught into dA, the flux of electric field, is equal to Q by epsilon naught, Q enclosed by epsilon. So this is first Maxwell's equation. This we have already studied in the electrostatic chapter, and this is called first Maxwell's equation. Okay, and similarly we have Gauss's law for magnetic field, which says that monopole does not exist. So Gauss's law for magnetic field B, which says that magnetic field B dot A, both of them are area. Okay, dA is area, dA is area. B is magnetic field, D is electric field, Q is charge enclosed, D is permeability, and this is equal to. Can you tell me, guys, what is B dot dA? What is the Gauss law for magnetic field? Who will tell me? Very quick. Okay. That's correct. That's B dot dx. That's also right. One of the formula. But B dot dA, aerial is zero. This is zero. That is why we say that monopole does not exist. Monopole does not exist. Okay. Don't worry. If you don't understand this law in much detail, when I come back to magnetic effects of electric current, that chapter I'll be telling you about this law again in much detail. Okay. But notice them now. And the third law is called as which was the third law? Shall I write it for electric field or shall I write it for magnetic field? Okay, I'll write for Faraday's law. Faraday's law. You know Faraday's law, right? What is Faraday's law? Is flux is equal to minus d phi by dt. You know this, right? Flux is equal to minus d phi by dt. But flux is nothing. What is flux? Flux is B into A. B into A, right? So I'll write B into A. Instead of writing flux, I'll write B into A. So, okay. B into. Acha. So, yeah. It should be length, right? So B dot dl, not area, B dot, acha, this is B dot dl is equal to 0, I suppose. Let me confirm once again. Is it dA or dl? Length or area? Yes, okay. So B dot dl is equal to mu naught I, mu naught I. This is Ampere's law. Okay, so let me erase this out. Yeah, I got it. Clear, clear, clear. So B dot dl is equal to mu naught I is called the Ampere law. This is called the Ampere law of electromagnetic field. Okay, so integral of B dot dl is called as mu naught I. Cool, right? Yeah. Yeah, that's correct. I'm right. B dot dl is equal to mu naught I. Yeah. So let me write it down very clearly. So I hope, guys, are you clear with the first two laws? So Gauss law for electric field is Q naught by epsilon naught, and Gauss law for magnetic field B dot d is equal to 0. That's all, completely fine. Nothing else. Okay. So there are two more laws. Okay, with respect to dl. So here we have dA, right? Both of them are area, and similarly have two different laws for length integrals. So first and fourth law. So we can write any law according to your comfortability. So one is Faraday's law, other is Ampere's law. There is Ampere's law. So Ampere's law is very simple, and we have seen this in already previous chapter, which says that integral of B dot dl is equal to mu naught I. You remember this, guys? So this is how we derived the formula for solenoid. What is the magnetic field of a solenoid? What is the magnetic field of a coil? Right? We already use this formula and derived, and this is called as Ampere's law. Okay, and the Faraday's law is integral of E dot dl is equal to minus d phi by dt. Yeah, now I'm right. Because what is E dot dl? E dot dl is nothing but EMF, right? Yeah, I thought initially I thought it was flux. That's not flux, it's what potential. So Faraday's law says that induced EMF is equal to minus d phi by dt. So I've written the same formula. But what is EMF, guys? What is EMF? EMF is equal to electric field into length. Using this formula, E is equal to minus dV by dr. Right. So therefore, uh, if you use this formula, potential dV will be equal to E into dr. See, that's what. Instead of EMF, I'm writing EDL, potential. Bas, okay. These are the four Maxwell's law. Okay, and these are very important. Can you notice one thing, guys? There is no name. First is Gauss law for electric field, second is Gauss law for magnetic field, third is Faraday's law, fourth is Ampere's law. There is no name of Maxwell, but we call it as Maxwell's law of equation. Why do we do that? Because James Clerk Maxwell was the person who took all of these four law and explained the complete aspect of electromagnetic radiation. Okay. For example, if you take Newton's laws of motion, it is not complete. You can't apply this to higher velocity. If you take general theory of relativity, you can't apply to lower velocity objects. No, that's not possible. If you take to If you take quantum mechanics, you can't apply this to very large objects. But if you take electromagnetic theory, electromagnetism, electrodynamics, you can apply to any conditions. So it's a completely well-built theory, and the person who gave the complete theory was Maxwell. Okay, so that is why these four laws are called as Maxwell's equation. He combinedly used all of these four laws and explained all aspect of electromagnetic radiation. Okay, and do you might ask me, sir, do I need to remember this formula? Of course. Why? Because we already know this formula. Gauss law for electric field. We already know this formula, derived many examples also. And same Gauss law applied for magnetic field gives me 0. So first two laws are remembered. They're very easy. Okay. Next, come back to these two laws. Using Ampere's law, I already derived magnetic field for solenoid and all those things, right? So B dot dl is equal to mu naught I, where I is total current here, the total current passing. Okay. And Faraday's law. Faraday's law is also we saw many times. EMF is equal to minus d phi by dt. But instead of EMF, I'm writing it as E dot dl. Both of them are same. Okay. EMF is equal to, if you notice this formula, EMF is equal to E into dr. That's all. EMF is equal to dV is equal to E into dr. Therefore, potential EMF epsilon is equal to E dot dl. Bas, okay. They're very simple. They're very simple, easy laws, and try to remember them as much as possible. And this flux is magnetic flux right here. Okay, cool, guys. So let me write it down very quick. Okay, E dot ds, the areal integral. D is area, E is electric field. This is equal to Q enclosed by epsilon naught. So this is Gauss law for electric field. Similarly, Gauss law for magnetic field. Magnetic field into area integral is equal to 0. Okay, but very simple, right? So moving ahead, if I clear this out and write E dot dl, what is E dot dl? E dot dl is equal to EMF, potential, and potential is equal to minus d phi by dt. So this is Faraday's law. We know this already. We have used this many times. So, but instead of instead of now, I'll not write V in between. That's all. E dot dl is equal to minus d phi by dt. Faraday's law, completely fine. And Ampere's law, integral of B dot dl. So dl is length here. Dl is equal to mu into total current. Mu naught into total current. Okay, if we compare here, as I had Q by epsilon naught, here I have mu into I naught. Mu naught into I, that's all. Very simple, okay. Remember that. And why am I writing total current here? Are there different kinds of current? Of course, there are different kinds of current. Okay, the best example is displacement current. Okay, for example, okay, so this is the last concept. Pay attention very clearly. So for example, in a wire, if the current is flowing, that is called as conduction current. So what is a conduction current? Conduction current is a current which flow in a wire. Very simple. Okay, in a regular copper wire, in a copper conductor or a metallic conductor, the current which flows is called as the conduction current. It is called the conduction current. Okay. Now imagine have a circuit. Imagine have a circuit which is which have a capacitor in between. Okay. So in this wire, conduction current is flowing along the wire, so completely fine. But in between the capacitor, there is air or dielectric material. I place a non-conductor. If you remember, usually I always place a non-conductor. So then, how do you think the conduction, the electricity is moving from this plate to this plate? In between, there is no metal, there is no conductors, there is no free electrons. So I have kept a dielectric in between. So how do you think the current will pass? The current is passing, of course, right? We have studied all of this already. If the current is not passing, then there is no, this becomes an open circuit, but it's not an open circuit. The current is completing the loop. So in wire, current is flowing in the form of conduction current. In between the plates of capacitor, the current is moving because in the form of electric field. Okay, see if you notice here, in the capacitor initially I was getting conduction current, and some said it has positive charge and the other side has negative charge. Electric field move from positive plate to negative plate, and we get current due to electric field also. Current due to electric field is called as displacement current. It is called as displacement current, and the total current therefore will be written as, so let me write a displacement current as id, and that formula is epsilon naught d phi by dt. Okay, and it is electric flux by dt. So there is no derivation for you, so just remember the formula. Displacement current is equal to epsilon naught d phi by dt. Bas, okay. Therefore, I can write the total current is equal to conduction current plus displacement current. Okay. Whenever there is conduction current, there will be no displacement current. For example, if you see here, there is only IC everywhere else here. There is only IC everywhere here, right? Okay. In capacitor, there is no IC, but rather than have ID. ID is equal to IC. They have both of them are same magnitude, but when ID is present, IC is not present. When IC is not present, ID is present. Cool. And this is a formula for displacement current, epsilon naught into d phi by dt. Cool. So make a note of it, or when I upload the notes, remember this and take a note of it. Okay. So lastly, this is the Faraday's equation. Aerial integral of electric field is epsilon naught q by epsilon naught. Aerial integral of magnetic field is 0, and E dot ds is equal to d phi by dt. That's what I wrote, right? E dot dl is equal to minus d phi by dt, Faraday's law. And lastly, I used to write the Ampere's law as B dot dl is equal to mu naught into I total, but instead of I total, I'll read it as I conduction plus I displacement. And what is mu naught? Mu naught into I naught as it is, conduction current, plus what is displacement current. So mu naught I'll multiply to displacement current. Okay, and I'll expand this formula. Mu naught IC plus mu naught epsilon naught d phi by dt. Bus. Okay, so this is the final form of last law of Michael Faraday. Okay, this is the final form. Cool, guys. That's up with the concepts. Okay, not much. So I hope make a note of all the formulas, 6 formulas which I've learned. These 4 Faraday's formulas. Okay, and C is equal to F lambda, and C is equal to 1 by root of mu naught epsilon naught, and C is equal to E by B. So remember these 3 formulas. And energy is equal to H nu. Energy density is equal to half epsilon naught E square. Energy density of magnetic field is equal to half B square by mu naught. So remember all of this. Okay. Cool. Bus. Okay. And along with this, if you remember this one, completely fine. Okay, so last we come to uses of electromagnetic radiation. So where do we use this radiation? So radiation, for example, radio waves, right, which have very large wavelength, we use it for communication, for all India radio, for communication of regular messages, and as well as communication through satellites. Okay, it is usually used for satellite, LL. Okay, for communication, Okay, and what happens to microwave? After radio waves, you come to microwave. Microwave use it for cookings, right? Cook snacks, right? To use to cook, to heat up things, and also it is used for communication. See, always the nearby radiation will have similar properties. Okay, so here I used only for communication. Now I can use this for communication as well as for cooking. Okay, for heating an object. For example, in the bakery, if you ask for a hot for hot lava cake, then they do is they heat it up and they give it to you, right? Or if you ask for a samosa, they do heat it up using a microwave. And if you go to infrared rays is again used for heating up. See, the nearby have similar properties, right? Infrared is nothing but makes up heat. It's a form of heat energy. And after heating up an object, the next spectrum what we get is the visible light spectrum, which enables us to see. So this is where our vision comes from. Okay, vision comes from electromagnetic radiation of visible lights. So later on, if I move to other end of visible light rays, from the red side to the violet side, I get ultraviolet light rays. And ultraviolet rays is very harmful for bodies. So if you get exposed for a longer time, it will cause sunburns. I mean, like it can cause cancer also. And ultraviolet rays are very harmful. That is why ozone layer protects our Earth from ultraviolet rays. That is why we can stand outside for a longer time. Otherwise, we could not stand outside in very hot sun. Okay, so next, as I move from ultraviolet rays to X-rays, X-rays are what will check whether our bones are broken, or even engines, right? Petrol engines and diesel engine, they can scan uh, those engine for internal damage using X-rays. Okay, and later on, if I go to gamma rays are most strong electromagnetic radiation. They're very dangerous. Okay, they can cause ionization in skin. They can cause cancer also. Okay, I mean they're really strong. Try to don't go near them. Okay, try to stay away from them as much as possible. Okay, they're really dangerous. Okay, so by this I could easily say that the chapter of electromagnetic radiations is completed. Okay, so next up we'll be starting with communication systems, but I'll do that for today. I mean, sorry, for tomorrow. So what are different kinds of communications, um, and like what are technology we use? I think I can complete that in one day. Again, tomorrow it will be done. Okay. So if you are continuing the classes, I think we can complete the syllabus very easily without any problem by the month end of January, right? We'll be left only with 2 to 3 chapters remaining. Other everything else will be completed without any issue. Part 2 will be completed very easily. Cool. Okay. Okay. Please, Anusha. So what I did was I uploaded all the notes today morning. Okay. So if you check now, I hope you can see the notes. If you think any notes is missing, you can drop me a message. Okay. I uploaded all of them. YouTube guys, am I clear? So that's all for today. We can end for today. Cool. I have uploaded all the notes and I have made a new folder for electromagnetic radiation. You can notice there. Okay. Cool. Okay. Oh, that's all then. If I forget to upload now, just remind me. I'll upload. Okay. Because like few work I'll be part of in few work. Sometimes I might forget to upload. You can remind me anytime. Okay, to upload a notes. I'll do that. Okay, then that's all for today. If you have any doubts, you can ask me, or we can leave today. Yeah, and submit the NPS before you leave. NPS is mandatory. Okay. Okay. Any doubts? Oh, there's a person called Vishalas. Oh my God, seriously. I did not notice it. I'm noticing it now. From YouTube, there's a person named who has the same name as me. Cool, bro. Clear. Yeah. Okay then. Okay, Bhargav. Okay, bye. See you later. Vishalas, bye bye. I'm saying bye to myself. Nice. Cool then. Bye guys. Take care. Okay. I'll see you with the next class. So I'll be ending the stream. See you all later. Bye bye.